A painter on top of two ladders. Two ladders, L1 equals 4 meter and L2 equals 3 meters long, are hinged at point A and tied together by a horizontal rope H equals 0.9 meters above the floor. As we can see in the figure, so they're hinged at point A, 90 degrees angle here, and 0.9 meters from the ground we have a rope, horizontal rope. The ladders weigh W1 equals 480 newtons and W2 equals 360 newtons respectively, and the center of gravity of each is at its center. So this one is at 2 meters, this one is at 1.5 meters. Assume that the floor is freshly waxed and frictionless, so there is no friction force on the floor. Part A, find the upward force at the bottom of each ladder, and part B, find the tension in the rope. So we're going to start with this, and in the next video we will look at part C and part D. Okay, so we need to concentrate on this geometry. Now we see that we have a 90-degree angle here, 3, 4. So this is a 3, 4, 5 triangle. So we obtain for this angle theta here, tangent of the angle, tangent theta is equal to 3 over 4. So this is a 3, 4, 5 triangle. Well, in order to calculate the torques for each forces, we need to find perpendicular distances, so we need to work on this geometry a little bit. Now, notice that this rope was attached, so let's check. The horizontal rope is attached at a vertical distance 0.9 meters above the floor. So at a vertical distance 0.9 meters above the floor, if this is the same angle tangent theta here, 3, 4, 5 triangle, if this is 0.9, this should be 1.2 and this should be 1.5. So that's 3, 4, 5 triangle again. And the center of gravity for this ladder is at 2 meters. So we have 1.5 this portion, therefore 0.5 this portion. Okay, so then we have 1.5 and 2 here. So we can see that from similar triangles, this is 0.9. This is going to become 1.5 divided by 2 is equal to 0.9 divided by this part. So this gives us 1.2 for this portion. And once again, this is a 3, 4, 5 triangle, 1.2, 1.62. So we can use this 3, 4, 5 triangle instead of the similar circles as well. If this portion is 2 corresponding to 5, 2 divided by 5 is 0.4. 0.4 times 3, 1.2, 0.4 times 4, 1.6 is this portion of the right triangle. This was already 1.2, so we have 0.4 remaining here. Okay, now this is basically 2 plus 2, 4. Once again, we have a right triangle here, 3, 4, 5 triangle. So 5 is corresponding to 4 meters here. So 4 divided by 5 is 0.8. 0.8 times 3 is 2.4. 0.9 is this portion, so this is 1.5. And here we have 0.8 times 4, which is 3.2. So this part was 1.6. This part should be 1.6. And once again, these two are the same. These two are the same from similar triangles. This should be 1.6. This should be 1.6. And if I go to the other side, I have the weight at the center of gravity at a distance 1.5 from the contact point P. 1.5, 1.5. Now, you can see that this angle theta, this is 90, 90 minus theta. This angle is theta. Once again, I have the 3, 4, 5 triangle here. So if this part is 1.5 plus 0.9, 2.4, that's corresponding to 4. 2.4 divided by 4 is 0.6, multiplied by 3 is 1.8. And these two should be the same, so I have 0.9, 0.9 here, 1.5, 1.5 here. Once again, from similar triangles, if this is 2.4, this should be equal to 1.2. Now you can see this whole thing is 2.4, and this is going to be 1.2. Okay, So the total distance here is then from 3, 4, 5 triangle 5 meters, and the distance here between the center of gravity of the left ladder and the point of contact P for the right ladder with the ground is going to be equal to 1.8 plus 1.6. That's 3.4 meters. So this distance, total distance, is 3.4 meters. Now that we have solved this geometry, we need to look at the forces acting on these ladders. The two weights are at the center of gravity. There's the normal force from the ground, and in general, we're going to have a contact force at point A, the hinge. There will be a vertical component and horizontal component. Now you can see that the only horizontal force acting on this ladder is the tension, so this horizontal force should be the tension as well. That is balancing this one, the same magnitude. And similarly, the same tension appears here, so this horizontal force should be on this part. And then there will be a vertical force, so this is a force couple on the two ladders. According to Newton's third law, it's an action-reaction. So the force on the left ladder FL is in this direction. The force on the right ladder FR is in this direction as we sketch it. Okay, now the first task was to find the upward force at the bottom of each ladder. So I start with the net force on the y-axis should be equal to 0. And this is my coordinate system, XYZ coordinate system. So I can see that for the two ladders considered as a total system, I have the two normal forces acting on it. So I have N sub L plus N sub R. And this is equal to the total weight W1 plus W2. W1 and W2 are pointing downward, and L and R are pointing upward. This is a force couple, so it cancels if I consider this whole thing as one system. So two ladders considered together. So this is left plus right ladder considered as a single system. If I write the net force on the x-axis, that is equal to 0, and I can see that for both of these ladders, T minus T should be equal to 0. So this checks. I can see that the horizontal components of the contact forces should be equal to tension, so that I'm going to get a balance at the end. Now, if I consider the net torque with respect to point P, so I'm going to use one of these contact points as the reference point to consider the torque. As you know, at equilibrium, we should have the torque with respect to any point equal to 0. So what is the torque at point P due to all of these forces acting on the system? So if I look at the normal force on the left hand side, it has a perpendicular distance 5 meters with respect to this point. So R cross F shows me that using the right hand forefingers pointing in this direction curled towards N sub L, the thumb points into the board. This is a negative torque because it's a clockwise sense of rotation. So I find that the first contribution is from N sub L minus 5 N sub L. Then I have this force W1, which has a torque with respect to this point P. So I can see that the perpendicular distance between the point of application of W1 and point P is 1.8 plus 1.6, 3.4 meters. So I have 3.4 multiplied with W1. What is the sense of rotation? It's R cross F. The sense of rotation is basically counterclockwise, so it's a positive torque. So this is plus 3.4 W1. Okay. Since for the system of these two ladders, the two tensions will have the so they're basically parallel to the ground, and they do have a perpendicular distance 0.9, but one is going to be applying a torque in this direction, the other one in this direction, so they will cancel each other. So you don't have to consider the torque due to these two tensions because they will cancel each other. And similarly for this force couple. So what I need to worry about is this W2, which has a perpendicular distance of 0.9. So R cross F shows me that the sense of rotation is counterclockwise, so it's a positive torque. So I will have plus 0.9 W2. And this should add up to 0 at equilibrium. Now W1 numerical value is 480 newtons. W2 numerical value is 360 newtons. So I can solve for the normal force on the left. N sub L is equal to 3.4 W1 plus 0.9 W2 divided by 5, and that gives me, for the normal force on the left side, 0.68 W1 plus 0.18 W2. And if I substitute the numbers, I will obtain N sub L is equal to 0.68 times 480 plus 0.18 times 360. So this will give me N sub L is equal to roughly 391 newtons. That's the numerical value I'm looking for. How do I find the other normal force? Well, I can use this equation. N sub R is W1 plus W2 minus N sub L. So N sub R equals W1 plus W2 minus N sub L. This is W1 plus W2 minus, for N sub L, I have 3.4 W1 plus 0.9 W2 divided by 5. All right, so this gives me, for N sub R, 5 W1 minus 3.4 W1, 1.6 W1, 1.6 W1 plus 5 W2 minus 0.9 W2, 4.1 W2 divided by 5. So I find that the normal force on the right side is 0.32 W1 plus 0.82 W2. And you can see that NL plus NR is equal to W. All right, the total weight. So NL plus NR, 0.32 W1 plus 0.68 W1 gives me W1. 0.18 W2 plus 0.82 W2 gives me W2. So the total of NL and NR gives me W1 plus W2, the total weight as expected. All right. And if I substitute the numbers here, N sub R is equal to 0.32 times 480 newtons, that was W1, plus 0.82 times 360 newtons, W2. So I find that N sub R, the normal force, is roughly 449 newtons. All right. Now, part B asks me find the tension in the rope. Okay, so to find the tension in the rope, I'm going to consider the torque with respect to point A. So that the hinge point here. So that will eliminate these contact forces. All right, so let's start doing that. The net torque with respect to point A, I need to look at each force individually and find the perpendicular distances. So N sub L has a perpendicular distance 3.2 meters with respect to point A. So 3.2 times N sub L. The sense of rotation is R cross F clockwise. So I obtain a negative torque contribution minus 3.2 N sub L. Then for the tension, I have a perpendicular distance 1.5 with respect to point A. So 1.5 times T R cross F. That gives me a counterclockwise sense of rotation. So it is positive torque. So I obtain plus 1.5 T. Then I consider W1. The W1 here is basically at a perpendicular distance 1.6 meters with respect to the contact point. The sense of rotation is R cross F. The sense of rotation is counterclockwise, so it's a positive torque. So this gives me plus 1.6 W1. And these are all the forces acting on the left ladder that will have a torque effect, and the total torque should add up to 0. This is only considering the left ladder. Okay? Or I could have used the right ladder, and that gives me the same result. So this gives me an equation for tension. T is equal to, let's write this here. T is equal to 3.2 N sub L minus 1.6 W1. So I take these to the right hand side, divided by 1.5, and that is now I can use what I know for N sub L. 3.2 times N sub L. N sub L is 0.68 W1 plus 0.18 W2 minus 1.6 W1 divided by 1.5. So this gives me a tension of 0.576 W1 plus 0.576 W2 divided by 1.5. So I find that the tension is 0.384 W1 plus W2. Now if I substitute the numbers, this gives me 0.384 times 480 plus 360 newtons, so that the tension is roughly 323 newtons. So that's the numerical answer to part B of the problem. Okay, so far in solving this problem, the first thing I did was to recognize these 3, 4, 5 triangles and try to find perpendicular distances with respect to certain points. So I started out with noting that the center of gravity is at the center. So this is 2 meters, this is 2 meters, this is 1.5, this is 1.5 meters where I see the weights. The rope, horizontal rope, is at a perpendicular distance 0.9 here. Since tangent of this angle is 3/5, I can use 3/4. I can use the same information here. 0.9 over 1.2 is 3/4. So then this becomes 1.5 and this portion becomes 0.5. once again, this is another 3, 4, 5 triangle. So the 5 part is 2, so this is 1.2, this is 1.6. And then I use basically this information here, the same distances, 1.5, 1.5 here. This angle theta, this is 90 degrees, 90 minus theta, theta. Tangent theta is 3 over 4. So I find that these two distances should be 0.9, 0.9, and this is 1.2 because it's at the same distance from the ground here. So if this is 1.2, then this has to be 0.9, and this is 1.5. Again, 3, 4, 5 triangle. This is my right angle here. So let's draw this right angle here. And then I see that this is 0.9, then this has to be 0.9. This is 1.2, then this has to be 2.4. Okay, now I consider both of these letters together so that the force couples cancel. The force couple appears at the hinge point here. The horizontal and vertical components, they have no contribution. On the set of these two letters, I have the two normal forces pointing up and the two weights pointing down. So I find this equation. And the net force on the x-axis should be equal to 0, implies that if there is a tension on this rope, horizontal force, it has to be balanced by a horizontal force on the hinge point. So there has to be a horizontal component with the same magnitude T pointing in opposite direction. The same argument applies here. So if I consider the torque with respect to point P, then I have a perpendicular distance 5 meters here, 5 times n sub L. I have clockwise rotation, so it is negative torque. Then for W1, I have a perpendicular distance of 1.8 plus 1.6, 3.4 meters. 3.4 times W1, the sense of rotation is counterclockwise, so this is positive torque. And for W2, I have a perpendicular distance 0.9 times W2, sense of rotation is counterclockwise, it's positive. This is a force couple, so they will have the same contributions canceling. And for the tensions, I have the same thing, same perpendicular distance, different senses of rotation, so they will be canceling. Okay, so this gives me an equation for one unknown, n sub L, and if I solve it, I obtain this answer, and I can substitute the numbers to obtain 391 newtons. In finding n sub R, I can use this relationship from the free body diagram of the two letters together. N sub R is the total weight minus n sub L, so that gives me the answer I'm looking for. Now, if I want to calculate the tension on this rope, I can consider the torque with respect to point A for individual letters. For example, for this letter, the net torque with respect to point A should add up to 0 because this letter is at equilibrium, it's not moving. So the perpendicular distance here is 3.2 meters for this force, so 3.2 times n sub L, clockwise rotation, negative contribution to the torque. For the tension, I have a perpendicular distance 1.5 meters, R cross F, the sense of rotation is counterclockwise, so 1.5 T, positive contribution. And for W1, the perpendicular distance with respect to the pivot point is 1.6 meters. R cross F gives me a counterclockwise sense of rotation plus 1.6 W1. So this is the equilibrium of the left letter that I'm considering here. So from this equation, since I know what n sub L is, I can pull out the tension, and the answer I obtain is about 323 newtons. And in the next video, we're going to consider the force on the hinge point A, and also we will see what happens if there is a painter standing on top of these two letters.